Well, good evening, everybody. And who's here has seen the recently released pictures from the James Webb Space Telescope? Round of applause. On behalf of the Paterson Museum and the National Park Service at Paterson Great Falls National Historical Park, I want to welcome you folks here in front of me today at the museum, as well as those of you at home, to join us for an evening of discovery. Paterson, New Jersey has always been set up as a city of innovation by Alexander Hamilton over 250 years ago. And today we're going to continue that tradition. We are an official host site, NASA official host site, to celebrate the first images of the James Webb Space Telescope. And we are lucky to have two experts here today who are going to talk a little bit about the telescope, and as well as one of the things the telescope will basically tell us is, could there be life out in the universe? So as many of you know, the James Webb Space Telescope was launched on Christmas Day of 2021 with a purpose to find the first galaxies that formed in the early universe and to see stars forming planetary systems. Today, as you know, the pictures were released, and this is just one of a few celebrations that we're going to have at the park. There's one tonight, followed by a family activity day on August 28th, so please check out information on that. And maybe we might be able to get another telescope viewing sometime in the late summer, early fall. So hopefully that will come to fruition. Without further ado, I'd like to introduce our first speaker today, Mr. Mike Greene. Mr. Greene was born and raised in Paterson, New Jersey, and he graduated from Eastside High School in 1968. He worked in the chemical and pharmaceutical industry for about 43 years. He's always been passionate about all aspects of space exploration, since the historic flights of Project Mercury, and possesses an extensive knowledge of NASA's staffed and unstaffed missions from the past to the present. Mike has been an official NASA Solar System Ambassador, volunteer since 2019, and enjoys turning his passion into action by promoting NASA's human and planetary exploration programs to his friends and neighbors in the northern New Jersey area. His goal is to convey to the same sense of pride and excitement that he feels for this wonderful journey of exploration in which we are all participants. Mr. Greene.
Thank you, Elise. It's great to be back home. It's been a while since I've been to the museum and my hometown in Paterson. I hope I give you some good information tonight. My name is Mike Greene. I am a NASA Solar System Ambassador. Tonight I'll be speaking on the Webb Telescope first images. I'm sure most of you have seen them already, but I'm going to go over some of them again with a little bit of history of astronomy. First thing I have to say, though, when I turn my head, I can't talk into the microphone, so bear with me. I always have this disclaimer I have to put up there. It says that I am not an employee of NASA or any of its contractors. I am a volunteer. I do not speak for the agency. Any opinions that are expressed are mine and mine alone. If you're not familiar with the Solar System Ambassador Program, it is a real thing. It's funded by a National Aeronautics and Space Administration. It's managed by the Jet Propulsion Laboratory in Pasadena, California. Those are the fine folks who landed the Perseverance rover on Mars last year. And there's about 1,000 ambassadors nationwide. And since the creation of the organization, I want to make sure I get these numbers right. We've reached more than 10 million people directly and almost 500 million people indirectly. And I think that speaks very, very well to the program. It's our 25th anniversary also. So astronomy was humanity's first science. And for several thousand years, This was our best view of the universe. That's the Milky Way galaxy, the backbone of the night. And then in the early 1600s, astronomy took a monumental leap forward with the invention of the telescope. And this is one of the early scopes. Now, while we don't know the true inventor of the telescope itself, in the early 1600s, a fellow by the name of Hans Lippershey actually applied for a patent, and there were patents back in those days on a telescope that could enlarge objects 3 times their size. And then in September of 1609, the great Galileo Galilei conducted the very first observations of the cosmos. So just in a few months, he discovered the rings of Saturn, the primary moons of Jupiter, called the Galilean moons, the hills and valleys of our moon, the phases of Venus, and he was the first person to observe sunspots. And that was in the 1600s. So we just check out the evolution of ground-based astronomy since then, from the 17th to the 21st century. And if you look at the last one, that's the Gemini array in Chile. And you can see they use laser pointers to look at the sky. And then astronomy advanced again in 1958 with the creation of NASA. NASA's early advancements were in airborne astronomy. These were several aircraft that were used as telescopic platforms. It started with the Galileo 1, then the Learjet Observatory, and then the Kuiper Observatory. And then came a great machine called Sophia, which unfortunately will no longer be flying after September. Sophia is the stratospheric observatory for infrared astronomy. Its first light, not first flight, but first light was in May 2010. Final mission will be conducted in September, just a couple of months from now. The decadal survey for astronomy decided Sophia was not worth the annual cost, and NASA went along with it, and project will end in September. So here's Sophia flying off into the sunset. But for the last time, you get to see its primary mirror being deployed. So then came space-based telescopes, and from the late 20th century right into the 21st, NASA and several other international space agencies launched a variety of space telescopes. Can't mention all of them during this talk, it would take too long, but 4 of them, NASA telescopes, are held in the highest regard. Of course, it's Hubble, Compton, Chandra, in Spitzer. These are gamma ray pictures taken by the Compton Observatory. If you're familiar with gamma rays, there's a episodic event that takes place in the universe called gamma ray bursts. And besides being sucked into a black hole, these are the most dangerous events in the cosmos. You don't want to get in the way of a gamma ray burst. It will literally tear you apart. And these are some pictures of Chandra in the X-ray range. All the white rings you see here are X-rays from exploding stars, novae, things such as that. These are infrared pictures from Spitzer. This is important because James Webb also operates in the infrared realm. What's nice about the IR scopes is that they can actually look through the clouds of dust and gas out there in the universe and can find the heat sources that you really can't see using the visual astronomy. Of course, the great Hubble Space Telescope continues to operate to this day in its 32nd year of operation. And these are just a few of the major pictures that Hubble took over that time. It's hard to believe there's actually an instrument out there now that surpasses Hubble, but there is. As I mentioned before about infrared observations, this is the famous Pillars of Creation in the Eagle Nebula that was taken by Hubble in the visible light. The other one is an infrared. Now, as nice as the one in the visible light looks, the infrared picture actually steers through the dust and clouds that are within the pillars. You can actually see where the new stars are being born. You can't see them in the visible light. You can't see them in the IR. But there's a cluster here and here. If you look in the visible light, you don't see them. So that's why NASA decided early on the next generation telescope would be infrared. And this is the famous Hubble Deep Field. This was the first deep field from 1995. This is looking back about 13 billion years. Since then, Hubble had come out with two other deep fields, the Hubble Ultra Deep Field, which went back to 13.1 billion, and the Extreme Deep Field, which went back to 13.2. But actually, this is the most famous image of the deep field. And virtually every point of light that you see on that screen is a galaxy. Very few stars at all. And the interesting thing is these pictures were taken over the course of about a 12-day period. People looked at one patch of sky, the southern sky, the constellation Fornax, is the furnace. And from ground-based observations, it was pretty empty. You really couldn't see much there. So Hubble appeared at the Fornax constellation for a period of about 10 days, about 1 million seconds worth of observation time. And was able to peer back from an area that we thought didn't contain much of anything, thousands and thousands of galaxies in this one little patch of space. And that just gives you an idea of how many, the limitless number of galaxies that truly exist out there. Because we didn't think anything would go over there and get it. And then you see what happens. So now we'll move on to the James Webb Space Telescope. The Webb scope is actually a collaboration amongst NASA, the Canadian Space Agency, and the European Space Agency. It's not strictly a NASA project, but they handle the bulk of the operation, research, and building of the instrument. The question I always get is, who's James Webb? James Webb was NASA's second administrator. He served from 1961 to October 1968, leaving just before the Apollo landing, lunar landings took place. Even though he was more of a businessman, he saw the reason NASA should have a balanced space program, not just to concentrate on human flight, but also on scientific. And he had the idea for a large space telescope very early on in the mid-1960s, and eventually that became Hubble. And then once Hubble was in orbit, NASA already started looking down the road for the next generation space telescope. And that was the original name of the instrument that eventually became Webb. In 2002, then NASA Administrator Sean O'Keefe renamed the NGST, which was Next Generation Space Telescope, to the James Webb Space Telescope. As I mentioned before, it is a project with NASA, the European Space Agency, and the Canadian Space Agency. The initial budget for the NGST was $500 million, and launch was scheduled for 2007. When Webb launched last December, the cost was just under $10 million. And actually 14 years behind schedule. But better late than never. There was a lot of doubt actually in the mid-2010s whether Congress was going to cancel the Webb project, but the astronomy, the scientific community, the astronomy community in particular, worked very hard to keep Webb. It does pay dividends for all the employees of both NASA, its private contractors, and different universities that contribute to the studies. Yes.
So it was supposed to be launched in 1997 or 2000.
Yeah.
Okay. What was it? Was it made already? Oh, so that's why it's 10. I was going to say, what the heck? It's sitting on the shelf.
No, this was not off the shelf stuff. This is brand new. The technologies, even today, listening to the press conferences this morning, even the people who actually run Webb now can't believe they actually put this thing up. It's so far advanced than anything other than that. So these are the mission facts. The prime contractor was Northrop Grumman. It was launched on Christmas Day of 2021. The launch vehicle was the European Space Agency's Ariane 5. Two reasons why we chose Ariane instead of one of the U.S. launch vehicles. Number one, the ESA said, go ahead and launch on Ariane. We will charge you for it. They are a partner, and that's one reason NASA decided to go with Ariane. Very powerful launch vehicle, 2.9 million pounds for us to take off. And the other reason is the launch site. It's in Kourou, French Guiana, near the equator. And when you launch near the equator, you're actually taking advantage of Earth's rotation. You pick up a little extra speed. And any way they can get a little extra power on the launch for Webb, NASA is in full agreement with the Europeans on that. And the mission duration, they were looking initially at 5 to 10 years, but when Webb got out to the L2 Lagrange point and used so little fuel and everything went so well, they've extended the mission from 10 to 20 years now. And hopefully last even longer than that, much like Hubble is. These are the objectives of the mission. using infrared instruments. Webb search for the very first galaxies that were created. The timing, we believe, is only 200 million years after the Big Bang. 200 million years sounds like a long time, but it really isn't. And you look at in cosmic time, that's really fast. So we can look back approximately 13.6, possibly 13.7 billion years. Webb is hoping to see the very first stars as they blinked on, and the first galaxy formations, and hopefully planetary formations. So it's going to be amazing what it can do. It will determine how galaxies form, observe the formation of star systems in planetary systems, and it can actually measure the physical and chemical properties of atmospheres of different planets, exoplanets, as they orbit their parent stars. In fact, this morning some information was already released on that. Just a size comparison of the mirrors, the primary mirrors between Hubble and Webb. What I found interesting about this is that the mass of the Webb mirror was much less than the Hubble mirror. And the other nice thing about the Webb mirror is it's self-correcting. If you remember when Hubble was launched, it had a defective mirror. And it took, so that was launched in 1990 on the Space Shuttle Discovery. And it wasn't until December of 1993 that NASA could launch a servicing mission on the Space Shuttle to repair to replace the mirror, put some new optics on it, and actually give it a pair of glasses. Now, this is a statistic which I found very interesting, but I cannot confirm. I don't think anybody can. But they say Webb is so sensitive to infrared light, infrared heat, that it could detect the heat of a bumblebee at the distance of the moon. But I tried to find out, do they mean the distance of the moon from Earth, or Lagrange point 2 is 930,000 miles away. So just for the sake of argument and make it a little more interesting, I put down, I could be wrong on that. And this is Webb's launch last December 25th. During the launch, the great Rob Navius, the voice of NASA, called the launch. He was down in Peru for that. And he said, from a tropical rainforest to the edge of space. And that's exactly what Webb did. This launch was very successful. Everybody held their breath. I don't think I started breathing again until New Year's Day. This is a picture taken by the Ariane upper stage after it deployed Webb. Drifting away. And this is the route it took out to Lagrange point 2, 930,000 miles from Earth, a little over 1 AU from the sun. An AU is the distance between Earth and the sun, 93 million miles. And L2 is a stable point in space where it's sort of a Sargasso Sea. You can park something there and it won't move very much. Very stable. And also, this is away from the sun. Webb cannot look at any source of the inner solar system. It cannot look at the sun itself. It would burn out the optics, but Mercury and Venus cannot be observed. Everything has to be from Earth onward. Yes. In a way, it is because everything orbits each other, but it's really in a halo orbit around L2. We'll show you that in a moment, what it really looks like. This is the deployment sequence for Webb from launch until its arrival at the Lagrange 2. To go through all these mechanizations, it took about 29 days from launch to full deployment. So actually it went from this to this. And the very interesting part, and I was very worried about this, Webb had 344 potential single points of failure. And any of those could have doomed the mission. Unlike Hubble, which could have been serviced by astronauts, as you can see over there, Webb can never be serviced, can never have any visitor. It's on its own. The only potential visitor it might receive in the future, it does have a docking ring, by the way, is for a robotic ship to get up there and just move it out of L2 and then move for another potential future space telescope.
So 7 was wrong, all that money.
When I heard about that 344 single points of failure, my heart just stopped. And there was a video that you can still see on YouTube. It's called, I believe it's 29 Days of Terror, something to that effect. You can still find it. That went over everything that Webb had to go through from launch through deployment to its initial checkout. It's quite interesting, and thankfully, all the bad stuff that we thought might have happened didn't. So far, so good. So I mentioned the halo orbit that Webb is in at L2. This is a view of the plane of the ellipse, straight on, equatorial view. And you can see it's not stable in one spot. It does tend to move up and down a little bit. So the center of L2 would be over here. The Webb goes a little up and down, which is a good thing. It does give a little different perspective of targeting. You can almost do some triangulation of its targets. It's not in a fixed spot. The next slide, which I find really interesting, is the polar view of Webb at L2. From the center of L2 would be over here. And the distance that it orbits, this is called a halo orbit, is greater than the distance from Earth to the Moon. So it is really large. And then once the testing got underway, Webb sent back its first test images. This is a black and white image that shows the alignment of all the telescopic panels except for one. That one still, I'm sorry, that one still was not in alignment yet. And here's a picture of a star, a rather insignificant star in space. HD 84406. This picture was taken by the Spitzer infrared telescope. Not bad, not sharp. This is Webb's picture of the same star. What's interesting, you can always tell a star now on the Webb pictures because they have these star spikes. It looks like there's 6, but there's actually 8 because 2 come out radially. But every other dot that you see on that screen in that picture is a galaxy. These are galaxies that have never been observed before. So in a way, this was a deep field picture. But really, it was just to test the accuracy of Webb on that particular star as compared to the Spitzer. Now, this was the first deep field test image, and you can see again the objects with the spikes are stars. And everything else there is a galaxy. And again, these have never been observed before.
Galaxy. And there's a planet.
Most likely. That's the nice thing that Webb can do. That's a nice thing Webb can do once it identifies a potential planetary system. It can zoom in on the planets individually and do characteristics, spectrometers of the components of the atmosphere to determine whether they're happening or not. These are the targets that were selected for the first Webb pictures. Most of the pictures you see here were taken by Hubble. This was the first picture that was released yesterday by NASA. President Biden made the announcement. This is the Webb first deep field image. It goes home. I need this thing before I'm finished. It goes back, this particular image, about 13 billion years. Webb will go back much further than that. Again, this was the first shot. But if you look at it, you'll see something very interesting. It's a little hard, but I hope you can check it out. Everything there is a galaxy, but some of them look like they're kind of drawn out, stretched, elongated. That's gravitational lensing. There are gravity sources out there that are actually giving the impression. If you look at the photons coming in from 13 billion years ago or so, that's bent or stretched the galaxy itself to our eyes. The galaxies themselves are fine. They're not bent like that. That's just the image that we receive. But that does confirm part of Einstein's space-time continuum theory. So this gravitational lensing is a real thing. I'm not a physicist. I can't get into too much detail about it, but this first picture actually proves that it does occur. And then this morning, NASA released, sorry, question? I'm sorry. In a second. And Webb has done that already, and Hubble has a history of showing that. In fact, that's our fate in about 4 billion years if we collide with Andromeda. There's nothing we can do about it. Andromeda's on its way. I wouldn't lose any sleep. Oh, this is the Southern Ring Planetary Nebula. And even though it's planetary, it's nothing to do with planets. It's just the way these things are itemized. But you can see in this picture here, that's in the near infrared, just a little bit beyond visible light. The second picture is in mid-infrared. You can see some differences between the two. But basically, this is the death of a star. And you can see the shock waves as they move out from the star itself. Of course, in the background, you can see other galaxies. And one star. Now, you mentioned before how we can observe the atmosphere of exoplanets, planets beyond the solar system. So the first exoplanet that was imaged by Webb was, I'm sure the name right, WASP 96P. And this is in the atmospheric composition. Now, I don't want to get into too much detail here, but the important thing is they've already identified water vapor in that planet's atmosphere. The sad part about it is this is a Jupiter-sized planet orbiting very, very close to its parent star. It's closer to its star than Mercury is to our sun. It orbits its star in 3.5 days. It would not be a very inviting place to live or work. It would be very hot, but apparently with the water vapor, it's very humid, which is sort of like what we have outside tonight anyway. It's the difference. This is another photo that was released this morning. It's called Stefan's Content, a Galaxy Group. Now, you mentioned the question before of galaxies in collision. A little hard to see, but right there are two colliding galaxies. This light's a quintet. It looks like it's 4. But actually, it's 5. There's one here and one there. They are starting to tear themselves apart as they merge. The gases and the dust tend to congregate, creating star formation right over there. But also, eventually, there are 2 supermassive black holes, which are in the center of each of those galaxies will merge, gobble up everything in the area, and probably end up with just one galaxy, which will happen with the Milky Way Andromeda. And this is the most incredible picture of the day. This is the Carina Nebula, a area of dust and gas, and star formation area, similar in composition to the pillars of creation that we know from Hubble. If you look closely, you can see the star nurseries. And some stars that have already been ejected from the cloud. And if you saw the press conference this morning to release the pictures, 2 things are happening here. There is star birth, but also the birth of the stars giving off their own energy, their own, as they burst to life, they give off gas and dust. They're pushing back the Carina Nebula cloud, causing it to collapse. Now, this will take billions of years, but it's in a balance right now between birth and death. And that borderline is right over here. I think that's just an amazing picture. And so you're going to get better at this. So as I say, these 5 pictures are just the beginning of Webb's, the first achievements for Webb. Hopefully it will go on for the next 20 years or so. They're always out there. You can go to any NASA site, just plug in Webb photos, and you will be instantly connected to the Goddard Space Flight Center Technology Laboratory, wherever. You can do that with Hubble right now. You can do it with Spitzer and Chandra and Compton. This is all public domain stuff. You have access to everything. It's amazing the archives that NASA has that people just aren't aware of. All free. So NASA's not standing pat. These are 3 future-funded space telescopes. These are being built. They're on their way. Here's Spirex, launch in 2024. There's COSI, launch in 2025. And the next major one, the Nancy Drake's Roman Space Telescope, scheduled for May 2007. This was originally called the Wide Field Infrared Survey Telescope. I'm sorry about that. I can't find the sweet spot on this. This was supposed to launch before Webb. it takes, as it says, wide field. So it would study large portions of the sky. And if anything appeared of interest, then Webb would have zeroed in on these. Unfortunately, timing got off. Webb had to take priority. Nancy Grace got pushed back a little bit. But they will be perfect complements to each other. We still have a few more years to wait on. And the decadal survey for astronomy has already begun their selection for the next generation of space telescopes. These are 4 that have been proposed for launch in the 2030s. The 2 that seem to be most favorable, and I guess it comes down to which one is the most effective or the most return on investment, would be Luthor or Helix. And all of these scopes can work in different wavelengths from X-ray, ultraviolet, to visible light, and again, infrared. So as the late great Carl Sagan once said, I have to read this, I can memorize it. The cosmos is within us. We are all made of star stuff. You're the way for the universe to know itself. Now the James Webb Space Telescope will continue humanity's never-ending quest for knowledge. With that, I want to thank the National Park Service, the Paterson Museum for organizing tonight's event. I want to thank you all for attending. It's really great to be back in Paterson again after quite a few years. And if there's any questions, I'd be glad to entertain. Thank you. Any questions? For me,
How do they see the A telescope from the accepting to a black hole?
but it's a good question because we don't want to launch them toward a black hole. There is no nearby black hole to the Terran solar system where we are now. The closest one is the supermassive black hole Sagittarius A star, which is in the center of the Milky Way, but that's still several hundred million light years away. We don't have any problem with that. I don't think we're going to have any real experience sending any telescopes or probes of black holes for a very, very long time. So again, I think we can see both. How long does it take the signal to come back? From Webb? Oh, just a matter of seconds. It's only 930,000 miles away. Light travels 186,000 miles per second. So you're looking just a couple of less than 10 seconds. So in constant contact with Deep Space Network.
So this is really crazy. I'm just like
Oh, it's nuts,
getting
yes.
into this. So you keep talking about it going back millions of years.
Billions.
Okay, is this like time travel? Like what are you
In a way, it is time travel. We are looking, the potential for Webb is to look for the very, very first stars that blinked on 200 million years after the Big Bang.
But how can you see something that's strong?
Heat source. That's the beauty of the infrared. When those first stars lit up out of the clouds of dust and gas after the Big Bang, they gave off heat. Webb will be able to determine that. Yeah.
That's chill.
I mean,
I was just wondering if you could repeat the question after somebody asked. it.
Oh, okay.
Yeah.
Sorry about that. Any other questions I can repeat? Negative? Well, thank you very much. I really enjoyed this. I'm sorry about the microphone issues. It's a little more sensitive than I thought. But I really enjoyed this talk. I hope you did too. I do have a business card up here. If anyone's part of another organization, a school, another museum, a library that would be interested in talk on NASA's projects, it doesn't have to be web. I do a lot of talk on their human flight programs, robotic programs, planetary exploration. So if you want to just take the card and give me a holler, that'd be great.
I do it. What is it we were going to do that we can't do now?
Web. And so the question is, what can we do now that we could not do before with web?
No. We were supposed to go up to the falls and do something, but now it's raining.
Yeah, that was going to be the telescopic observations of the sky. Gary had a couple of telescopes we're going to try to set up. I guess we cannot do that this evening because of the clouds. Unfortunate because we're at the full moon for July, the buck moon. There's a new comet in the sky, the K2 comet, and planetary lineup is quite impressive right now.
And we would have been able to see through the telescope.
Probably.
Well, the person who has the telescope is actually going to be our next speaker, so you can ask him.
So we are hoping for something in August. Is that
Yeah,
correct?
we're hoping, yeah, it depends on Gary's availability.
Well, thank you all very much. I enjoyed it.
Thank you again, Mike. Hopefully, if I stand back a little bit from the microphone, maybe the audio will be a little bit better, you know, for folks at home. Before we introduce Mr. Gary Swangin, I did want to give a shout out to Paterson Museum's curator, Ms. Heather Garside, who's right over here. And is the reason why we are able to do this hybrid programming for the very first time. So, and Heather has some interesting events that she wants to introduce that are coming up here at the museum.
Thank you all for coming tonight. A little taller, please. We're really excited to welcome you all. As you know, we've unfortunately been closed to the public for quite a while here at the museum, so we really love having you guys back. We just wanted to let you know that this summer we do have a couple of events that will be coming up where we will be open. We are working with an organization called Wordseed Inc. here in Paterson that is a poetry-based organization. And they are actually going to be doing a summer camp this summer, actually this month, later this month, called Ocean of Possibilities, which is a one-week program for children geared towards teens, and that's completely free. 1 week of poetry where you're working with professional authors and poets. So we wanted to mention that. And then that event ends with the Friday night poetry event that they host here. So any students participating in the summer camp will be presenting the poetry here on July 29th, and it's also an open mic opportunity. And then we will be having another one of those programs August 26th, and they're called The Power of Words. And both of these flyers are going to be available at the front desk if you're interested. So thank you again for coming, and we'll have our next presenter.
Okay, thank you so much. So I wanted to introduce our second speaker for the evening, Mr. Gary Swangin. Mr. Swangin spent 16 years here in the city of Paterson as the manager and planetarium astronomer for the Panther Academy High School, which again is right here in the city. Gary is now embarking on a new career. He, along with his colleagues, have recently created the Belinda Educational Group for Science and Technology, which recently received its 501c3 status. One of the organization's projects is called the Smart Sky Program, which provides equipment and instruction for students who wish to learn about the universe, both in the United States and abroad. The telescope that Gary has will allow folks in light polluted areas to have nicer views of the sky than you would expect. Pretty much everyone here in New Jersey is in a light polluted area, so sadly it doesn't penetrate cloud cover from a thunderstorm, but if we are able to have a star party again, you will definitely be able to see things that you wouldn't have expected to see in a city like Paterson. Tonight, we are fortunate to have Gary provide information on alien life in the universe. He will be also talking a little bit about the telescope. So again, without further ado, Mr. Gary Swangin.
Make sure. You hear me okay? Okay. I picked this particular theme because in September, I'm going to be headed out to California to set up a very large telescope, which will be used for searching for exoplanets. What do we mean by exoplanets? Quite simply, any worlds or planets that are outside our solar system. Many of these exoplanets are very, very far away. And what I wanted to do for you tonight is to show you various techniques that astronomers use to detect these planets. Furthermore, after I complete this introduction to finding planets, exoplanets in the universe, I'm going to show you how you can actually participate in finding planets. Believe it or not, we do have a program called Citizen Astronomy, and it allows groups of people to use a telescope, which I'm going to show you in a few moments, and actually use it for actual research and communicate with other astronomers on how to find certain planets in the sky. I'll discuss the technique tonight on how you can be able to discover those planets and how even the Webb telescope is used to find exoplanets. Now, normally when I'm teaching this particular subject, it's in college, and it's really detailed. And there's several methods used for detecting alien planets or exoplanets. But I'm going to narrow it down to about 2 or 4 methods without getting into other stuff as well. Okay? So let me see if I can use this correctly. Yeah. Okay, James Webb Telescope. You probably know more about it than I do right now, and that's good. But one of the things that this incredible instrument is going to do is to search for planets elsewhere in the universe. Now, this is not something new. We've been doing this for 20 years. We discovered a considerable amount of planets outside our own solar system. So let's begin. In order to understand this, we've got to talk about the planets in our own system. And as you look, this is our planetary system. You notice that green line right there? All right. That's usually referred to as the habitable zone or the Goldilocks zone. Now, anybody know the story about Goldilocks? Tell me about Goldilocks. Okay, well, I have a little different version of that, but anyhow, Goldilocks goes into this house, and I'm sure all the adults know this, but just to be on the safe side, and she wanted to taste the porridge. Bears weren't there, and so what did she do? She tasted one of them, it was very, very cold, right? One was very, very hot. Okay, well, our planet Earth. You'll probably notice that it's in the right spot. It's not too close to the sun, and it's not too far away. In other words, our planet is 93 million miles away from the sun. It lies in what we call the Goldilocks or habitable zone. There's another way of describing that. It means that when you're in the habitable zone or the Goldilocks zone, it means that water can prevail. There's a place for water that can survive or exist on this world. It doesn't mean that it will be like a liquid ocean. It could be water, it could be vapor, it could be frozen. And it can exist in this different states, such as, water, ice, and vapor. And that's why we refer to that as the habitable zone, because if we have water on a world, there's a good possibility in the Goldilocks zone. Not too far from the sun, not too close to the sun, and have water on it, there's a good possibility that that planet may have life. Now, I know many of you will probably have been reading or hearing on the news that every time an astronomer discovers a planet, the person will say, there's going to be life on it. And it's not the case. There's a little bit more detail to that. Anyhow, okay, this is a better view of the habitable zone, not as crystal clear, but you can see where the Earth is just right. Okay. Now, the first thing astronomers do is not only do you discover those planets, or try to find those planets using different techniques, but afterwards we want to find out if the planet has the type of position around the star to reside in what we call habitable zone. Now, not all stars are alike. I'm sure you know that. If you go outside at night, you look at a red star, chances are you're probably looking at a giant star. If you look at a blue star, chances are you're looking at a star much hotter than the sun. Some stars are very hot, some are very, very cool, some are just right like our sun. Which means that the Goldilocks zone or habitable zone is not going to be exactly the same distance for every star. You discover a planet around it. It depends on whether the star is hot, depends on whether it's cold, and it also depends on the position of the planet. And what we've discovered, which is really surprising, is that we found giant planets very, very close to their stars. And that leads us to some very bizarre conclusion that maybe planets wander in the universe. Maybe planets change their positions in the solar system. We now hear this new terminology called moon planets. What that means basically is that we could find a planet not even orbiting a star, but a good possibility of this planet just drifting among stars in our Milky Way galaxy or elsewhere. Okay, let's talk about the methods for finding planets. Keep this in mind. This is not very difficult to measure. It's quite simple when you think about it. You can perform even experiments at home to prove this. Okay, here we go. First method, it's called planetary transits. Planetary transits. What is that? Well, let me give you an example, an everyday example. Okay. Let's suppose you look at a car with its lights on at night. And all of a sudden, something moves in front of it, moves in front of that light. Or let's say a bird flies in front of it. Okay? What happens to the light on the car? It diminishes, dims for a brief moment. Now, this is what's going on with certain stars. If we discover a star, when we look out at certain stars, if there's a planet going around it, of substantial size, the light, that planet is going to block out the light of the star. And watch this. Here is an illustration showing such a thing where a planet goes in front of a star. Now, this is a real cool method. The only reason why I like it is because, well, if you look at several thousand stars at once, you can point out those stars that have planets. You'll see the ones blinking, so to speak. You'll see the ones where the planet moves in front of the star. So in the case of the Paterson Telescope, or in the case of this James Webb Telescope, all they're going to do is take the telescope and put it in a large field of stars and look for all those stars that have little dark flickerings in it. And that will give you an indication that there is a planet going around. Okay. Now, what happens if you plot, I won't try to get too scientific with this, but if you show on a graph the light curves, what we call the light curve, And as the planet moves in front of the star, the light of the star diminishes, it gets lower. You can see by this curve here. Now, what is good about this is you notice that curve, that dip? That dip can tell you a lot about how fast the star is moving, about the planet is going around it. It can also tell you the time at which the planet goes around the star. That gives you its period. So knowing the period, knowing the mass of the star, we can calculate, using Newton's laws, the mass of that planet. And by calculating the mass of the planet, we can determine whether or not it has a sufficient amount of gravity to hold down an atmosphere. There's another good thing about it. By determining this path or this period, we can also determine the distance that that planet is from that star. So from just that blinking kind of thing that you see, we can actually measure a lot of parameters about a star that can be trillions of miles away from us. Trillions of miles away from us. It's amazing. Yeah. Here's an illustration. I think you can see this graphic right here, where you see the planet going in front of the star. Okay? And when it goes in front of the star, you can see that the light of the star diminishes. Now, there's one problem with this. This is assuming that the star is at the same plane that can cross the plane of that, well, excuse me, the planet can cross the plane of that star. I mean, if the planet is going like this, we're not going to be able to detect that. Let's assume that the orbit is along our line of sight for this to take place. Now, we set up, about 20 years ago, we set up Kuiper, the Kepler telescope, I'm sorry, not Kuiper, Kepler telescope, and it went out and looked for stars, other planetary systems. And using the transit method for the Kepler telescope, as well as for other methods that we're going to be talking about, we picked up a tremendous number of planets outside our solar system. Here's the graph or that of this illustration showing the position of the Kepler telescope in the direction that it's looking at. If you go out tonight, not tonight, at night, if you go out on a crystal clear night and you look in the constellation of Cygnus and Swan, adjacent to the Cygnus and Swan is the constellation of Lyra and Harp. And right between, just about between those two stars, the M star on the cross of the Swan, and that white star Vega, the constellation of Lyra, is the direction where that telescope, rather, where that spacecraft is pointing. And it's picked up so many different exoplanets. Take a look at this. Thus far, using this method of transits, we have discovered 3,902 exoplanets. That's a large number of planetary systems. Okay. The next method, which I kind of like, is called the radial velocity method. This may sound a little complicated, but I'll see if I can break it down, make it easier for you to understand. If you take a look at this next illustration, you'll be able to see this. I'd like to go up and if I can point to this. All right, here's the planet. Excuse me, here's the star, and this is the planet. Now, do you notice something about that planet? Something weird now. It's wobbling. You see it's wobbling like this because it's got this gravitational pull. Would you believe that the planet Jupiter exerts the same kind of gravitational pull on the sun? And the sun wobbles, not as you see here, but it does wobble. And its speed is about 8 meters per second that this wobbling takes place within the sun. So here we see an extreme situation whereby the planet has so much mass that it causes that planet to wobble, that star to wobble. Now, the wobbling, now, you see it wobbling, but if you're, let's say you're standing right here and you look at the star approaches you. and then it moves away. So if I'm standing here, of course, this is not a scale. If I'm standing right here, I see the star, one point of the star is coming towards me, and the light of the star is moving away from me. So what we do is we just look at the chemical composition, which we call the spectra, of the star. And we notice that the star spectra shifts towards red and shifts towards blue spectrum. And when it's shifting towards red, it shows that the star is moving away from us. And when it shifts towards blue, it shows that the star is moving towards us. Here, take a look at the spectrum. That's another illustration of this. On this radial velocity here, you can see the star moving away from us, right here, in this direction. And then it's moving towards us, and the light is shifting towards the blue or shifting towards the red. Let's see if I can show you the spectrum. There you go. And you can see those lines right there. This is the red part of the spectrum. This is the blue part of the spectrum, the violet part of the spectrum. When those lines slightly deviate towards the red, that means that the star is moving towards us. And when it deviates slightly to the other side, it means the star is moving away from us. And you say, well, what does all this mean? Well, if you can time, if you can look at the spectrum and have a clock and time how take a measured period of which the star is either coming toward you or away from you, then that means you can tell how long a planet is going. It actually gives you a proof that there's a planet actually doing this tug of war with the star. And many, many planets have been discovered this way. And if you know the period, you know how long this takes place, you can measure the mass of this planet, and thus it can be. We've used this method quite a few times. This is 51 Pegasi, one of the first stars that I've ever done using this, what we call the radio method. And we found out something quite extraordinary about this star. It is so close to its sun that in only about 3 to 4 days it goes around it. So this pattern that you saw is very, very rapid and takes place anywhere between a little bit over three days, closer to 4. And this is bizarre. A world about the size of Jupiter, sometimes referred to it as a hot Jupiter, so close, only a few million miles away from its parent star, it only takes a few days to go around it. Now, think about what I said earlier. You think this would be a place to have life? Probably not. It's so close to that star, we measured that its temperature is about, on the surface, is about 2,000 degrees Fahrenheit. So very, very good. Another one is, this is crazy. Every time when I look at this video on this particular planetary system, there's about 5 or 6 different pronunciations. Whether it was Lisa, Lise, Gleis, whatever, you pick whatever you like. But this is another solar system, another planet was discovered around it using the Kepler Observatory telescope. And again, another planet that's been discovered, one of the first planets discovered around this particular. Moving on. Using this method, we have discovered 947 exoplanets. 947 exoplanets. And what is really interesting about this method is we're now able to determine the mass of very small planets, Earth-sized planets. This tells us that there are many, many, many Earth-sized planets in our Milky Way galaxy. Furthermore, it tells us that there are probably in our own Milky Way galaxy more planets than there are stars in the sky. How many stars are there in the Milky Way? Our galaxy? About 200 billion. Think about that. There are more planets in our Milky Way galaxy than there are stars. And then if we ask the question, look, you guys just saw earlier, all those galaxies, clusters of galaxies. Ask yourself the question, how many other worlds exist in the universe if there are billions of other Milky Ways or other galaxies? This is, I think this was brought up a little earlier, called gravitational microlensing. Simply this. From Einstein's theory, we know that space is curved. The force of gravity can actually curve space. So, using this technique, we're able to determine whether a star has a planet around it. Let me show you this. Okay. Here you can see. Here's an object. Here's a star. Give you a galaxy. What's going on basically is that object is behind this object. Okay? So when the light passes by this particular object, the force of gravity bends curved space so that what you see is the object here and the object up here. Right. In other words, you would see 4 different images of that object that lies behind this particular object. Right? Let me show you. There it is. These 4 objects are behind this particular. Right? The object's behind there, and the light that's coming from it is being bent by this. Now you may say, all right, so big deal. How's that going to help us find the planet? How is this method going to help us discover another solar system? Well, if there's a planet around here, by the time that planet orbits that particular star, it adds more gravitational pull to the light that's coming from behind that star. So we see a little fluctuation in the light due to the fact that the planet contributes to distorting, adding more gravitational pull, and causing the light to bend a little bit more. And this technique is used quite extensively, not only for exoplanets, but used quite extensively for discovering other galaxies in the universe. Because we see other galaxies behind galaxies that are closer due to this process called gravitational microlensing. Okay, with this method, we've discovered 89 exoplanets. So you may ask now, wait a minute, you have other methods, and we do. We have pulsar timing, Einstein's effect, all kinds of different methods beyond this. We even look at black holes, or we look at rotating neutron stars, and we can see that other exoplanets, other planets are disturbing these rotating stars, the period at which these stars are rotating. So how many exoplanets have we discovered thus far? About 8,000. 8,000 other planetary systems. Out of the 8,000, NASA has reported that exactly 5,180 of those planets have been confirmed. So going back 8,000, we think they exist, that we've already detected. But for sure, we have 5,000 that we actually confirmed. 5,000 other worlds. Now, James Webb Telescope is going to do the transits. It'll probably do some of the wobbling, and no question about it, it'll do also gravitational microlensing. So that number is going to increase in terms of exoplanets quite a bit. Okay. Here's another method, the last method. It's called direct imaging. And this is something for many years astronomers always wanted to do. What happens if we could just block out the light of the star? Put something in front of the star and block it out so that we can see other worlds going around it. Now, there's a problem with this because stars are very far away. I mean, take a look at the closest star, other than the sun, which would be the Proxima Centauri system. That's about 4 light years away, or about 24 trillion miles. 24 trillion miles. If you were traveling on a spaceship like the Apollo, which travels 25,000 miles per hour, it would take you about 133,000 years just to reach the nearest star. It's only 4 light years away. So how can you do this? I mean, what kind of technology do we have to employ to do this? Well, we have larger, better telescopes out there. We can put discs in front of some of the nearby stars, block out their light. And when we do this, guess what? We actually see other worlds going around some of the stars that are relatively close. And you're going to notice they're kind of like a reddish tint. The reason they have a reddish tint is because those stars are reflecting heat radiation from their parent star, which means that what we're doing is we're looking at those planets in the infrared. Now, we know that the new telescope that we put up there is going to be searching for things in the infrared. Whether they're going to use this particular method, but I don't know yet. But I'll find out pretty soon whether they're going to use this direct imaging. But this is currently being used, and we discovered many more. Okay. Now, with direct imaging, 100 planets does. Now, how many of those planets, of the 5,000 planets that we have confirmed, how many of those planets are Earth-like? Out of those 5,000 planets, we've got about somewhere between 40 and 60 planets that we know are in the habitable zone, and we have detected atmospheres around those planets. And it looks very, very much that these particular planets have, in some form, water on them. If they have water, if they're in the right place from their parent stars, then there's the possibility that life may exist. I call this stranger things. From our study of exoplanets, we've come up with the most bizarre stuff, bizarre solar system that we could ever possibly imagine. Let me show you. Okay, we've discovered what we call hot Jupiters. Now, this is kind of weird. We kind of, for many, many years, we always thought that the larger planets like Jupiter, Saturn, Uranus, and Neptune, these are called gas giants. And those gas giants are located very far away from the sun. They're on the outer levels, outer regions of the solar system. Jupiter, for example, is somewhere about 520 million miles away from the sun. But since we have used these techniques in finding exoplanets, we've discovered that many of these giant planets that we would expect to be in the outer regions of the solar system, we've determined, or actually we've detected large giant planets closer to their stars. Now this is strange to us. It may imply that planets may not be stationary in their long life around their parent stars. They may be what we call planet migration. Planets can change their position in the solar system. So finding a hot Jupiter, which is a very massive planet, close to its parent star, is baffling astronomers. What is going on? Here's something else. Now this is really bizarre. Remember, I think, you remember in Star Wars, Skywalker was on the world. We kind of laughed at that. I think some of you remember it. It's on this planet. And he looked up and they saw two stars, two suns in the sky. Anybody remember that from Star Wars? 2 stars? Well, we laughed at that. Oh, come on. We got 2 stars in the sky. Well, laugh no more because we're seeing a lot of that. You see right over here. Here's a planet going around 2 stars. We've actually found that happening. Even more bizarre, we found a planet and a star going around another star. There are all kinds of weird combinations that we've discovered thus far with looking at these exoplanets. Okay. Now, like to give you the opportunity to participate in finding planets in the solar system, I mean, outside the solar system. And the way I'm going to do this, is show you this telescope. This is the one we were planning to use tonight. Sorry about that. Well, we're definitely going to do this very, very soon. Okay. Now, this is in November. It's in Arizona. It's a larger telescope. I put this guy on. This guy is called Serena. Serena is the newest telescope, newest technology in astronomy. When I say the newest technology in astronomy, is you take this guy, you put it in your backyard or on your patio. You operate it by using an iPhone or an iPad. It does things that you will not believe, but I think the proof of the pudding is going to show you some of the images that I was able to get with this telescope. Okay, it's not cheap, I'll tell you that. $4,000. But you know, if you go, I have a larger telescopes, all kinds of equipment. When I add up the price of all the stuff I've added to the bigger telescopes, the price is just about the same. So this is nice. Now, I was hoping to demonstrate this for you, but I'm going to show you what I got with this thing. We started a program in our organization called Smart Sky. There's our website. You can go there. Let's get all the information about it. And what we're doing there. We're going to have these telescopes distributed, hopefully nationwide, to certain organizations and Park Service, if we're hoping urban areas, because these things tend to be used in the city to extract pictures. I'm going to show you something from the city, okay? So I want you to see that, okay? Yeah. Okay, that's me. I guess you don't. I have two scopes. This is Selena. The other one is from the college. They let me use that for about a year. And that is called EV scope. They both do the same thing. You can see they're not very big, right? It's about the same price, by the way. All right. And they're both made in France. But anyhow, I carried one of them, Selena, out to Arizona. And I'm going to show you the Arizona pictures, and I'm going to show you some stuff in New Jersey, right? Okay, there it is. That's the Andromeda Galaxy. Photographed that. The time it took me to do that was 30 minutes with that telescope. And that's a picture of a galaxy about 2 million light years away. You can see the nucleus and you can see the dust trails around it. And it wasn't difficult at all. And what's nice about this particular scope, I'm not trying to sell these things to you. This is not a commercial. The nice thing about it, you set it up, you tell the telescope to look up in the sky, and it automatically knows where it is. And once you get it in position, you get a catalog. And it'll say, these are the things that are available in the sky. You press the button, the telescope goes there. It tells you how long it's going to be looking at it to get a decent image. And you will see a thing called stacking. Some of you may know something about what stacking is. If you take a photograph, several photographs of an object, you take, and Sony has developed this process in many of their cameras. A lot of the digital cameras are doing it this day. You probably know it will take 3 or 4 exposures, and then you combine those exposures to give you the best image. Well, in this case, this image was 130 shots, 130, 140 shots, and it was stacked automatically by the telescope. And this is what you get. You can send it to your iPhone. You can actually send the image to a friend of yours, or save it, or whatever you do with it. I've blown them up and hang them all around the house. Okay. All right. This is, anybody know what this is? No, it's not the crab, but you have seen this thing naked eye so many times it'll make you cry. This is the Orion Nebula. The Orion Nebula. And this was taken in Arizona, all right? Now, I don't want you to think that New Jersey doesn't have a decent sky. Here's New Jersey. Okay? And that was taken in the city. Okay? So these folks actually work in Paterson, New Jersey. Now, I think the question was, should we go out tonight and take a look? They're not that great. I mean, you know, they can do it, but you got to have a little bit of good stuff. But these work very, very well in New Jersey, no problem whatsoever. I've taken so many different images. Here's another one. Oh, this is one of my favorite. This is N13 from the constellation Hercules. This particular cluster this is about 25,000 light years away. That light takes 25,000 years to go there. I like this particular cluster because there's about a half a million stars all close together with one another. Great cluster. This was one of the clusters that was used when we sent a message out from Arecibo down in Puerto Rico. We sent a message there in 1970 to this cluster. And in this message, it was an interstellar message that gave whoever that might be able to pick up our signal, our DNA, our location in the universe, how many people are on the planet Earth, whether it tastes good in case we want to But that's M13. It's a really easy thing to see, even with a pair of binoculars. What I'm going to do when I'm with you guys, I have a green laser pointer, which are great when you're pointing up into the sky. I'm going to point to this thing in the sky for you. And if you have binoculars, you're going to be able to look at it. You're going to think that you're an astronomer right away. And then we're going to use this guy. And here's another thing about this telescope. You can share the entire observation with 20 other people. So if you bring your iPhones or your Android device, all of us, or 20 people at once, can actually see these pictures develop, okay? So it's really cool thing. Oh yeah. You saw the image of a planetary nebula, which was taken by the ones that was released today. They were taken by the James Webb Telescope. Well, this is not James Webb, but this is another planetary nebula which was taken this is from the constellation of and this is very, very far away. This is an exploding star. This is a star that is losing its envelope. The gases are moving out somewhere between 20 and 30 miles per second. And it's going to be continuing doing that for many thousands of years. But again, you can photograph this stuff with an instrument like this. Oh yeah, this is the last one. I took this one about from New Jersey. You might want to know where I live. Okay. I live in Warren County, 3 miles from the Delaware River. It is a little dark, but this is an Orion. This is called a flame nebula. This is hydrogen gas. You can see it in large quantities, many trillions of molecules. There's a bright star in front of it. It was taken with this telescope, and the exposure was 15 minutes exposure. Again, with this one of these telescopes.
Is it set the exposure or
It decides for you. You don't have to do anything. And this will make you feel really helpless. But you can actually set the telescope up and plan where the telescope is going to be in the sky and wake up the next morning and have all the images. Now, I know that's terrible, but let me tell you something. When I'm using the big telescopes out in California and down in Arizona, rarely look at an object in the sky. The bigger the telescope, the less time. No one goes to an observatory, a big observatory, where their astronomers want to get their PhDs and all that stuff. The bigger the scope is, the less. Don't really go and look through the telescope anymore. That doesn't happen anymore. You got too many instruments tied to it. And the telescope that I'm putting out in Arizona, excuse me, in California, is being remotely operated in Delaware by the University of Delaware. So they're going to control the telescope, and they're going to do all this wonderful stuff, exoplanets, photographing things like that, but never really looking. So I hope I've helped you out with a little understanding about how we find planets. I hope I've sold you on using smart scopes. Take a look at our website and you'll find out other things. We're also working on some other projects that are designed to educate young people, college students, and other people in the field of astronomy. Thank you very much. Oh, anybody have a question? Any questions? Yes. Yeah. Yeah.
One object that was given gravitation.
Yeah, one object.
One object.
Yeah, behind the other object. Yeah,
They're all the same.
all the same thing, like mirror images. If you want to try that, okay. The reason why I'm saying this, I gave this lecture at a winery, and it was great. I mean, the wine was great, but what I did was I asked everyone to empty their glasses, which they gladly went through the process. If you hold the wine glass up to a light, because the wine glass is curved, you will get multiple images on it. And that was the way we described gravitational microlensing. So go home and drink your best vino and try this experiment. It's a lot of fun. Yeah. Yeah, any other comments, questions? Okay, thank you.
Thank you again, everybody, for coming out today, braving the weather, braving the Zoom to celebrate the release of James Webb first images. Excuse me. On August 28th, we're going to have another event at the park. It's going to be more of interactive activities, hands-on activities, round robin style, geared for interested parties, especially those with kids, to experience and explore the science behind the James Webb. So look for more information on that on our Facebook page and website on August 28th. And safe trip home. Thank you so much.